Okay, so now we want to talk about the quantities of interest, which are conditional means and marginal effects, but they're going to be conditional means and marginal effects of different objects. Depending on what case you're looking at. So if you're looking at data censoring, you would really like to have the an expression for your regression line for the data censored, the censored value y star, or the latent variable y star. Well, that's a variable of interest, right? I mean, if you think about back or wealth coding example, or top coding of wealth example, what if you actually observe that entire distribution of y star? That would be your dream scenario, right? And so in order to make predictions about what that distribution is, well, then you would just need to know what beta is, right? Then you completely nailed it, because the conditional mean of y star given x, well, that's just equal to beta, right? Because y star, that was equal to x beta plus some epsilon, but then the conditional mean of epsilon given x, that's equal to 0, because we have a normal distribution with mean 0 conditional on x. So that's what we get in data censoring. So really in that case, we're just interested in estimating beta, okay? Because we observe x, and we're done in that case. Now in corner solution outcome case, that variable is not of particular interest, okay? This latent variable doesn't, I mean, maybe you can give it some kind of utility meaning, but it's really like, it's not the observed outcome it's the observed outcome that are of interest, right? So if you think about the number of hours that people are supplying in the labor market, well, you don't care so much about the latent number of hours. They're not, being put into use, right? You want to see what is the expected value of y conditional x. What is the expected amount of hours for, say, a person with this education or this age and experience, and so on and so forth, once you condition on that, right? And that turns out to actually be a nonlinear object. It's not equal to x beta. We're going to derive that now, what it looks like. It depends. And then also it could be, you wanted to calculate what is the conditional mean of y, say the labor supply, conditional on your observables for the people who are already in the labor market, who are participating, okay? And what are the probabilities that they're not participating, or what are the probabilities that they are supplying in a positive number of hours, okay? So, the probability for participating in the labor market, for example, these two coefficients here, these two objects here will also be of like structural interest. And then also how x changes each of these objects. So the partial effects of these. So these are the kind of things would be interesting. And you see here, it's our interest in the data censoring case is really on the latent variable. We would like to make inference about, or also that part of the distribution that we don't really observe. Okay, whereas here it's much more about expectations and conditional means of the observed variable y. So that's a big difference. Okay. And we haven't put in any functional forms of this, but that's a whole deal. That's what we're going to derive. And then really, when you calculate partial effects, you really have to think about, are you in one case, is it data censoring case, or is it Common solution outcome case you're in? Okay. And you also see these data in the latter case for Common solution outcomes, the effects of the regressions really actually becomes depending on x, because all these things here are not just x beta, they're nonlinear functions of x and beta. Okay, so the marginal effects, they can be derived and computed, and we're going to do that. Okay, and which effects you look at, depends on your application, and you have to be precise on what that is. Is it data censoring, or is it corner solution outcomes? Okay, we're going to look at each of them. So here's a bunch of slides, there's 6 of them, that derives all these things, and if you just trust me, you can just fast forward. Okay. So, well, these two cases, probability of y equal to 0, probability for being at the mass point, or probability being the continuous part, well, that's easily calculated completely in the analogous way to what we did for the Tobit model. So I'm not going to dwell too much with that. You got the probability of being positive being the standard normal evaluated x beta over sigma, and the other one, you got that one. You can derive these things. from basically using exact same arguments as we did for the probit. So this should be well known at this point. Now, the conditional mean of y given x, that's a little bit more tricky, okay? Because we need to derive a number of different objects. So what we do is we first use the law of iterated expectations, essentially just saying that you can you can split up a conditional mean in these two different cases where you either first condition on say y being in the lower part of the distribution, or y being the positive part of the distribution, and then you just wait with the probabilities that these two things happen. Okay, that's totally legal. It's just, you know, moving around with conditional expectations and probabilities through the law of iterated expectations. So this, I'm not using really the structure of the model here. I'm just using like standard statistics. Now let's look at the first part here. That is the conditional mean of y given the y is negative. Okay. Now that's the same as saying as y star is negative, but when y star is negative, y is equal to 0. Okay. So this guy here is just equal to 0, right? So we don't have to care about this part at all. Okay, whatever it's multiplied to, it's 0. Okay, because these guys here are this guy is 0. Then you have the latter part, which is the conditional mean of y given that y star is positive times the probability that that is the case. Okay, so this is what we end with. We know this guy, well, that was 1 minus the CDF of the standard normal, this guy down here, but we need to compute the other guy. Okay, we need to compute this one. Okay, so let's do that now. And so here's a derivation, and so what do we have? So the first thing I'm doing, realizing, is that whenever y is positive, the observed value of y is positive, then y is equal to y star. So I could just, you know, substitute in y star for y, okay? And y star, that's x beta plus u. I think I'm missing up notation. One place it was called e, I guess, but you know, e or u, whatever, it's the error, okay? And then we need still to condition on then y star was positive, so that's the same here. Again, we still condition on x, but now since basically because of the independence between u and x, this really simplifies. First of all, because x conditional on x, well, that is known, right? So you can move that guy outside essentially the expectation operator, and then you're left with essentially u conditional on y star being positive. And so you don't, but then it turns out because the independence between u and x, you don't need to condition on x anymore. So you are essentially left with this expression here, which is the conditional mean of a normally distributed variable, conditional that normally distributed variable is greater than some threshold that is known. So x beta. Okay, so this is the conditional mean of a truncated normally distributed variable. Okay, and we have formulas to calculate this. And again, here, this is a little bit of a digress, but I think it's instructive to see where this is coming from. So I'm not just throwing it at you, okay? I'm zooming out a little bit so you can see the last one. Okay, so here's, we now want to calculate a little bit of calculate the conditional mean of a truncated normal. So here's a truncated density, okay? So that's what we're gonna look at. We need to calculate the mean of a variable that has a density, right? So what is that? Here's the original density that we're looking at of interest, but then we divide by, in order to make this condition that the random variable is greater than some threshold, well, then you essentially, you take divide with the conditional, with the probability that that is the case, which is essentially 1 minus the CDF of that distribution evaluated at C, right? That's the probability that set is greater than C, okay? So basically you can say we really need to make a normalization here, because otherwise that density does not integrate to 1, right? If it just suddenly just start to remove part of that distribution, it has to, the conditional density needs to integrate to 1, otherwise it's not a density, right? Now suppose that set here is normally distributed, okay? then we just replace these densities and the CDF for that distribution with those from the standard normal distribution. And so that's what I'm done here. Okay, so this is the conditional density for a standard normal distribution. And then you can calculate the conditional expectation by integrating that epsilon, that random variable over its distribution. And I put in here phi of put in here our conditional density, what we just derived, and then it turns out this integral has this nice closed form, and you can actually, I'm not going to dwell more with it, but it really it's integrating from C to infinity only on the support of that distribution, right? Again, I mean, essentially, when you let this guy here go to infinity, well, then basically anyway, this part here yeah, I'm not going to talk more about it. What I would just want to say here is we have this conditional mean is equal to this expression, and so now when I put it in, now we know what it is. It's really a conditional mean of a standard normal distributed variable that is truncated to be above some certain threshold. So we'll use this, and then remember what we had. We had in our we had u, the conditional u was greater than sigma that minus x beta. So we're gonna rewrite a little bit. So we're gonna make a divide through with sigma on both sides and then multiply outside. That's all right. We can do that, right? But then now this is standard normal distributed, and we can use our formula that we had before. So our conditional mean for a standard normal distributed variable with a truncation point of minus x beta over sigma. So we put that stuff in here, and then essentially because of the symmetry we can of the normal distribution, we can rewrite this in this following way. Okay, this is called the inverse Mills ratio. It has this particular functional form. It's a function of the explanatory variables. And now you see that this conditional mean, well, that's x beta plus something, okay? And that x beta plus that something makes that if we start to differentiate this guy here with respect to beta, well, or with respect to x, we're gonna get beta plus something that depends on x because this is a nonlinear function. So we don't have like a constant partial effect anymore, okay? Because yeah, because of the nonlinearity of that conditional expectation. So that was a conditional mean of y being positive, y when y is positive. Now we can then combine this to get the overall conditional mean, and recall that from our exercise with the conditional or with the law of iterated expectations, we arrived at this expression here for the conditional mean of y. So it was a conditional mean of y that when it's conditional on it being positive times the probability that it is positive. And then we just put in our expressions, what we just derived, x beta plus sigma times the inverse Mills ratio times the probability of having a positive outcome. You can move this a little bit around, but the bottom line is, again, now suddenly got expressions that depends on nonlinear on beta. So if you take the derivative of this regression function here, well, it's not going to be beta. It's going to be beta, and a bunch of other stuff that depends on x. Okay, we'll look at it in just a second. And then I want to say also a little bit, another thing here is if you take because of the convexity of the max operator, if you take the expected value of the max, right, you're going to get of this max operator, it's gonna be bigger than the max of 0 and the expected value. Okay, so you put in these things here. Here again, so this means that the expected value is going to be bigger than the max of x beta, which is positive. You can illustrate that. Okay, so it's always gonna this regression function here is always going to be bigger than the regression line had you observed the underlying latent variable. Okay, it kind of makes sense, right? Because especially in areas where there's a probability of being around the truncation point, you will have a larger effect. I'm going to illustrate that in just a second. Okay, So here's it, just a little bit of a summary of the results. So the first case, this data censoring case, that's an easy case where you just want to have X beta, okay? And then that gives you, constant partial effects. So once you have beta, you have your partial effects, okay? But the case for the corner solution outcome, we have all these different objects of interest. Okay, you got the conditional mean. Well, that depends on complicated function of x and beta, and everywhere here it's really central that we're using objects from the normal distribution, right? So it looks like this entirely depends on the distribution of the normal of the errors being normal, because otherwise you wouldn't have anything from the normal distribution here. Those expressions, then you got the similar one for the effects at the basically at the intensive margin, where people already say have a positive demand or a positive supply of hours. That's x beta plus sigma times inverse Mills ratio, and then you got the two probabilities. And we cannot just do OLS assuming that this is a linear function in beta, right? That was what we did on one of the very first slides. Say, what happens if I just regress y on x? Okay. Well, we just see here that that is a nonlinear regression function. It's not a linear regression function, so it's not equal to x beta. So you're not going to capture that with a linear regression function. Again, here, should you take to work with the data where you only have the truncated values? Well, you're making a selection, so you need to account for that by adding this additional conditional mean of the error term. So you got this additional error here that's correlated with explanatory variables, and you're going to get essentially because it depends on x. So if you exclude that, well, you're going to get bias in your parameter estimates. So what you cannot identify beta by simply regressing y on x using only the positive the observations where you have y that's positive. So you can't do that either. Okay, and that was what we saw in the very beginning, that you got bias estimates if you try to do so anyway. Okay, what you need to do is to basically take account for these nonlinearities during the estimation. You could do like nonlinear least squares using these regression functions, or you could do maximum likelihood just like we are doing. Okay, so here's a function that is in the code. It's called conditional mean, and it implements all these functions. So I have done that here. Again, I'm not going to dwell too much with it. Go in, look at the code. It's right there, and see if you can make the link. This is basically the functions that were written up on this slide here. Okay. So these are all the functions that are implemented in this mean, in this code. That's called conditional mean, and then you can get that. We're gonna plot those in just a second. Okay. I want to just also say a few words about more words about these corner solution outcomes. So you got the conditional mean here can be decomposed really into two effects, right? That's the effect for y when y is positive. That's what we call the effect on the intensive margin, and the effect due to a change in the number of people that has y positive. So if you think about, say, hours worked, that would be the number of people who are participating in the labor markets. So that's what we usually call the extensive margin. So you change policy, or you make a change. You make a change in the explanatory variables that motivate people to work more. Well, that could be two different effects. That could be an increased labor supply for the people who are already working, or an increased labor supply in terms of increased participation, which we call the response on the extensive margin. Okay, so this is an example, and you may actually be interested in both effects and decompose the overall effect in these two effects, right? What is the effect of the probability of participating, and what is the probability on the intensive margin? Then combine, you get the overall effect. Okay, and so these two effects, they're nonlinear, and therefore the partial effects are nonlinear. You can differentiate each of these. It's actually a nice exercise in algebra. You get all these different partial effects, and it's clear that none of them are just equal to beta, okay? One thing I want to say here is if you let, if you, for example, let x beta go to infinity, then you can see too from the previous expressions that basically the conditional mean is converging to the conditional mean of y star that's converging to beta. Okay, so that's and that's also the case for the for the those that are truncated. This is very intuitive, right? If you make x beta really big relative to sigma, well, it means that nobody is truncated anymore. So in those cases, it's gonna the y star, the observed variable is almost always going to be equal to y star, and so so the expectation is going to be equal to that underlying regression line. Okay, and you can see that here. So I've illustrated that here in a small example. So what you have here is basically. Here, the blue line, that's a regression line had you work with the latent variable. Here you got all your observations that are centered. You got basically, they continue down here, but then we don't observe that. They're truncated at 0, okay? And then this line here, what is that? That is the conditional mean of y when conditional on y being positive. Remember that I said this is always bigger than the conditional mean of y. And it's always bigger than the condition x beta. Well, that's where you see here, right? And so it's very intuitive, right? First of all, the conditional mean conditioning on that it is positive is going to be bigger than when you do not condition on it. Okay, but if you look at the shape where these things are turning out to be different, it's really in this area here where there's a big probability of being centered where they differ, right? And so that you need to take into account. What else can we say here from this? I think, well, another thing that we showed here was if you let x beta go to infinity, well, then both these conditional means, they are converging to the conditional mean of the underlying latent variable, that is x beta, right? And that's what we see here as we increase x beta. So down here you have basically x. So as we increase those, well, then they approach each other. And actually, you know, we can also illustrate here how these conditional means would completely overlap in case there was no censoring. So if we increase beta, well, then they start to become closer. If you increase it more, well, then they eventually they become, you know, identical in the case where there's no censoring, right? So you can move around these parameters, and you see in the limiting case where there's no censoring, then they're complete overlapping, and you could just estimate the model with linear regression. So yeah, anyway, I'm going to put it back to what we had to begin with, and so you see this picture here. Again, I just simulate data and then I'll make a plot. There's a function that does this. I don't want to go into how you plot different things. Okay, well, I want to say one thing before we continue. It seems like all these things, they can be calculated. You need to use these in different formulas, but in the case where you know centering, you don't need to do that, okay? All these things, all these conditional means, well, they depend on the normality assumption quite a lot, right? You got the CDF of standard normal here. You got inside this inverse Mills ratio. You got the PDF of the standard normal here. That's in there, in that inverse Mills ratio. You also got these everything here really depends on the PDF of the standard normal. So and we also assumed that the variance did not depend on x, okay? So how sensitive are our model to these assumptions? In the linear regression model, we know that that is not a big deal, right? We can still estimate the model even though the errors are not normally distributed. We get consistent estimates of beta. But if we have heteroscedasticity or non-normality in the Tobit model, you're going to get devastating results. That's what I'm going to talk about in the next video.